Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. I haven't advertised this series in a while. Maybe I should do it today. But anyway, this is a 3-volume series I wrote from 2019 to 2022. You can see pictures of the covers of each volume on this slide. The first 2 volumes are text. The first volume is more recreational. I'd say a little bit easier too. It's sort of advanced high school level math, but it's kind of fun math subjects, I think, including the ones I've been going over so far in this video series. I'm about halfway done with it. There's 10 chapters in the first book. And then the second book is more academic. This has 6 chapters, but it covers more advanced topics like calculus and various types of functions and probability and statistics. I'd say it's kind of first or second year college level. And then the third volume is just problems and solutions pertaining to the first 2 volumes. So that's what's in my series, The Math Lovers book. And you can find it on Amazon.com. You can either type The Math Lovers book or you can type my name, David Tare, and you'll find it there. And I think they're available both for in paperback and in Kindle, and I believe they're $30 or $40 each paperback, or $100 for the whole series, and I think it's $20 Kindle. I don't remember the exact price, but I think they're worth it. I mean, but if you don't want to spend the money, you can just watch this series for free and maybe learn something from me. Anyway, that's a little plug for my Math Lovers book. Now I'm going to talk about the continuum hypothesis. This is my 6th video, 6 out of 8 videos on section 5.6 of volume 1, which is on cardinal numbers of sets. I've been talking about cardinal numbers or cardinality. And I think I pretty much said everything there is to say already in my last lesson on the continuum hypothesis. This is going to be a pretty short video because I've already pretty much said everything. I'm just going to say it again and show the slide pertaining to it because I kind of jumped the gun last time. But anyway, so here's the continuum hypothesis written out. And as you'll recall, if you've been watching my last few videos, there's actually at least 2 infinite cardinal numbers. We discussed 2 already. There's the smallest cardinal number is called Aleph Null, Hebrew letter Aleph with a subscript 0 to its right. That just represents the cardinality of the counting numbers, which is also equal to the cardinal number of the integers or even the rational numbers. You get a lot of kind of paradoxes associated with infinity because it turns out infinite sets can be bijectively equivalent to proper subsets of themselves, as they are for instance, the counting numbers or the whole numbers or even or odd numbers or the integers, even the rational numbers. They all have the same cardinality, which is Aleph Null. But then I think yesterday I discussed a bigger cardinal number known as the Continuum and denoted as C, small lowercase c. And I proved that C is bigger than Aleph Null. So there is no bijection from, for instance, the counting numbers to the set of all real numbers. And the continuum is the cardinality of the set of real numbers, by the way. And you can use a very powerful argument called Cantor's diagonal argument, which I went over last time to prove this fact, this very counterintuitive fact. But then I think I touched on a continuum hypothesis. So you can define another cardinal number, Aleph 1. That's just defined as the smallest infinite cardinal number that's bigger than Aleph Null. And it's easy to define. You can even kind of construct sets whose cardinality is Aleph 1. They're pretty weird sets. I'm not going to go into that. I don't go into it in my book. But then for a long time, I think from around maybe the turn of the 20th century to about 1940, mathematicians were trying to prove or disprove what's called the continuum hypothesis. The continuum hypothesis states that Aleph 1 is equal to C. In other words, the cardinality of the real numbers is the next cardinal number after the cardinal number of the counting numbers. Pretty reasonable assumption, but it was very, very difficult to prove. And then finally in 1940, very famous mathematician named Kurt Gödel actually proved that you can't prove it, that you have to assume it. You have to make it another hypothesis of set theory. It's impossible to prove in the version of set theory that people were studying at the time. It's impossible to prove the continuum hypothesis. It turns out you have to add it as an axiom. Gödel proved that, and he proved that if you add it as an axiom, it's consistent with conventional set theory. So that was kind of a nice result, very unexpected result. But there have been other results like this in math. I mean, for a long time, in geometry, people are trying to prove in the 19th century the parallel postulate, which is the fifth of Euclid's axioms of plane geometry. It turns out, it's kind of the same status, I'd say. The parallel postulate has a very similar status in geometry as the continuum hypothesis does in set theory. I know a lot of set theorists don't agree with this. They kind of insist it's either true or false. But it turns out in Euclidean geometry, at least, you can either add the parallel postulate as an axiom. That gives you plane geometry, Euclidean geometry, or you can assume it's not true, and then you get curved geometries like Riemannian, which is the geometry of a sphere, or Lobachevsky geometry, which is geometry of a hyperboloid. Those are both legitimate geometries, and in both of those geometries, the parallel postulate's false. Well, it turns out that the set theory has very much the same status. You can either assume it's true, in which case you get one version of set theory. I think it's the more conventional. I'm not sure which is more conventional. I think most set theorists today don't like the continuum hypothesis. I think they prefer set theory without it. I'm not sure why they do. But I didn't even mention that it was in 1963 there was another mathematician, Paul Cohen, who proved that you could also assume the negation of the continuum hypothesis. You could assume that the continuum hypothesis was false, and if you do that, you get another version of set theory, but it's still consistent. I don't know why. I'm not an expert on set theory, but I know that my understanding is that most set theorists today prefer Cohen's version of set theory, in which the continuum hypothesis is false. I'm not sure why they prefer that. I really don't know. I don't know enough set theory to know whether or not it's better to assume it or its negation. Maybe they just like having other infinities between Aleph null and C. I don't know why. Maybe they like C to be Aleph 20 or Aleph 100 or maybe an infinite Aleph. I really don't know why they don't like the continuum hypothesis, but they don't. But, anyway, that's kind of the status of set theory and the continuum hypothesis. So that concludes my video for today on the continuum hypothesis. Thank you for watching. Long live math, and I'll see you guys next time. Bye.